And hello, welcome to vBrownbag US, the March 9th edition. Tonight, we are going to be talking about the CCNA-DC Section 2, Configure, Verify, and Troubleshoot a Switch and Internet Communications using Nexus. Whew, that's a mouthful. This evening, our presenter is going to be Brian Trainor. You can find him on the Twitters at BE Trainor. Some shop notes. If I can get this thing to slide over. Come on now, there we go. A couple of quick notes. Obviously, you can get in on the conversation on Twitter. We are at vBrownbag, and the Twitter hashtag is #vBrownbag. We have, tonight's is the US version. Our guest, again, is Brian Trainor. His website is Mount Virtual, and this evening I will be your host, Chris Williams. And so allow me to kick it over to Mr. Trainor, and we will get this thing going.
Great.
And go. Okay. You have control, good sir.
Okay, yep.
All right, and I can see your screen.
All righty. Fantastic. Okay. Well, welcome everyone. It's good to be here. This is round 2 for me. If you were here last week, then you got to hear me talk a lot about the kind of the basics and a lot of the foundational frameworky stuff of internet networking. So tonight we are going to be looking at objective 2, section 2 of the blueprint, which is primarily layer 2. Just real quick, a little bit about me. I'm primarily VMware focused in what I do, my day job. I think I'm probably along for the same ride as a lot of other people as far as using the vBrownbag really as an opportunity to better my own studies of the CCNA data center track. So anyway, so I'm learning this stuff as I'm going along too. So as we go through this tonight, just know that there might be some things that I don't know, but anyway, we should certainly have fun going through this. So let's go ahead and dive in. So with the first exam objective here is just talking about the technology and media access control method for Ethernet. So Ethernet. So Ethernet is okay. So Ethernet is really refers to the family of network products and protocols that's covered by the IEEE. And one of the things I think it's really neat, if I just want to pull up a chart here of just all the IEEE 802 standards. Okay, so they've got all kinds of different classifications, and some of these we immediately recognize, like 802.11 are the wireless LAN specifications. Some of the we're going to be talking a lot about 802.3 tonight, which is the Ethernet standards. And actually, we'll probably hit on some of the 802.1. You'll see as we go through some of this, some of like the bridging protocols and things of that nature. But anyway, this is kind of a neat chart here. If you ever wondered how much of the different network devices that 802 makes standards for, that's a neat little chart there. So we are going to dip into layer 1 just momentarily. So these are a lot of the different specifications that IEEE has set for the different types of cabling, the physical media. And so we've got our speeds. Some of this is historical, right? The thin net and thick net. We never hear those terms anymore. This is going to date myself, but I do remember using thin net back in my first IT job. Okay, we were stringing up a whole bunch of classroom computers and using a bus topology, just connecting a whole bunch of computers to a thin net line. So thankfully those days are over. We've moved on from that, much faster speeds. Now this list certainly is not exhaustive. That there's many other cable specifications that I didn't put on here. You've got like the 10G base SR and LR for some of the different fiber specifications. But I've noticed that just kind of a tip here. Some of this might just seem like, why do we really need to know the the formal IEEE standard name, 802.3an? Why do I need to know that? Well, I'm not really sure why you would need to know that particular terminology, but you probably will be tested on it. I think I remember some of those questions coming up on my route switch exam. So anyway, so just a little tip there. It's good to know this kind of stuff. So if we move on, so CSMA-CD, this is an important feature with an Ethernet. Okay, now we see this with collision domains, most certainly. Now, we talked last week about hubs that when, again, we don't use hubs any longer, but what hubs did were basically they were allowing multiple connections into a single, what we call collision domain, which means that multiple machines could be talking. Unfortunately, though, if they were talking at the same time, then collisions would occur. There's no way of really separating that traffic because, again, it's a collision domain. Everything that goes through there is just basically getting blasted out to everybody else that's on that network segment. So a collision domain, basically, in essence, is a section of the network in which multiple machines really need to be prevented from talking at the same time, because if they do talk at the same time, then collisions occur on that, and data is corrupted, and so bad things happen. So what we need to do is create a means of preventing those collisions. Okay, so and Chris, are you controlling my screen?
I am not.
Okay, all right. I just saw the mouse moving across, and I think that I accidentally clicked on the share screen, so I'm not sure if somebody else grabbed. Anyway.
Oh, let me fix that for you.
Okay. So talking about CSMA-CD, what this does is it basically prevents two devices from talking at the same time on this network segment. Okay, and the way that works is it's CSMA-CD. It's obviously an abbreviation. It stands for Carrier Sense Multiple Access Collision Detect. Okay, that's to take in there. The carrier sense is basically just means that each station or each node on the network there is continuously listening for traffic on the wire to determine when there are gaps between data transmissions. So they're basically waiting for the wire to be quiet so that they can then talk. Okay, so they're listening. The multiple access, you've got more than one device connected to the network. This also means that any of these network devices on that segment that they can transmit at any time. Any one of them can transmit at any time. Now, because of that, then as I said, there's a possibility of collision. So there needs to be a way to detect if a collision has occurred. Okay, so certainly they're waiting their turn, waiting for the line to be quiet. But if two devices on that network do talk at the same time, then a collision occurs. Once that collision occurs, the two sending devices are, they know that a collision has occurred, and so they then send a jamming signal to all other devices on that network that a collision has occurred, and basically tells everybody to stop transmitting. And then each one of those devices then will independently determine a random back-off time. Basically, it's this algorithm that runs, and so they'll each come up with hopefully a different back-off time before they can start retransmitting again. So the whole point there is to just keep them talking at the same time so that collisions don't occur. Okay, so this is very important in collision domains. It's also very important in half duplex links. Okay, so duplex settings. Okay, this is another another topic within the whole Ethernet specifications. So there's half duplex and full duplex. Half duplex is when on that network link that you can basically only have one, you can only send or receive at any given time. Okay, so even if you do have just one machine connected to, say, a switch, but duplex, well, that machine there can only send or receive at any given time. Let's say it's connected to another device. Each one of those can only send or receive at any given time. Okay, but they need to be able to have some mechanism for knowing if the other machine is talking or not, because only one can send or receive. So they use CSMA-CD to be able to determine if, okay, is the other one not talking? Okay, now I can talk. And so that way transmission can still happen in one direction at a time. Now, full duplex, on the other hand, means that you can send and receive at the same time. Okay, that uses double the amount of wires or wire pairs. Okay, that's one thing I didn't mention in the duplex is that half duplex the cabling that's used in the half duplex network link is essentially it's just using one pair of wires in that cable. Full duplex. If somebody's moving my mouse again.
That is me. Sorry. You clicked.
Okay. Yep, no problem.
There you go.
Yep.
Actually, there we go. Presenter can always take control. Yeah, I can't fix it. I can't unscrew that.
That's okay.
Actually, Graham has a question.
Yeah.
The question is there a jam signal? I thought that they just checked that the receive. I thought that they just checked that the received what they sent, and if they didn't, they did the random back off.
So from what I've read there, yes, they do send a jamming signal. Basically, it's to inform all other devices on the network that a collision's occurred. Okay, so it's basically telling everybody, hey, don't send anything yet. And then they go through their random back off time.
Okay.
Okay, so yeah, pretty consistent from what I've read. If that's incorrect, if somebody wants to correct me, absolutely. You know, I'm no expert on this, so. But that was my understanding.
Okay, I'll try not to mouse over the screen. Sorry.
Oh, you know, that's right. We were gonna check that. Do you want me to?
If you want to give it back to me and then I hand it back to you, that might fix it.
Okay.
Okay, so I'll make presenter, and now I will make you the presenter again. And
yep.
Check that, and there. Okay. Share your screen, and
yep.
Hopefully I've been disallowed all rights. Yes, I believe we're good. Awesome.
Okay, fantastic. All right.
I blame myself.
Well, no, I think I give control, but anyhow.
Blame the host. Come on now.
There you go. All right. So the cool thing about duplex, again, we can send and receive at the same time. Now, it does require a point-to-point connection. Cannot use full duplex on a link that has a hub. Okay. And again, full duplex doesn't use the CSMA-CD. If we're connecting to a hub, we need to have some method of knowing or some method of preventing a collision. Now, the other interesting point about full duplex is that so because we can send and receive at the same time, we can run at 100% efficiency in both directions, meaning that we can use the full bandwidth in each direction. So if we're using a gigabit link, full duplex, that means we can be sending 1 gigabit in one direction and receiving 1 gigabit at the same time. I know it's crazy, but that means that really we have ultimately 2 gig of aggregate bandwidth there. Now, that's in theory, right? I mean, that's just you're supposed to be able to get that. So take it for what it's worth. But the whole concept there is that yes, that you should be able to use full efficiency in both directions at the same time. And of course, most of our networking these days is using full duplex. Switches are going to auto negotiate anyway. All of our, everything up from 100 megabit and higher automatically uses full duplex. And then, certainly the cabling that we use it provides the pathways for that. So on to the next objective. So let's talk about the Cisco switches. Okay, so first of all switches use layer 2 address. Okay, so layer 2, we're talking about data link, as we learned last week, and the layer 2 addressing is essentially your MAC addresses. Okay, so if you remember last week, we looked at we talked about the layer 2 Ethernet frame header, and in that header of that frame, we would find the source and the destination MAC address. Okay, so a frame gets sent out, it's going to have the MAC address of the machine that, say that I'm trying to reach, and it will also have the source MAC address of my machine. Okay, now the MAC address it's a 48-bit number, 12-digit hexadecimal. So I've got a sample one down there, and the first portion, the first 6 digits, or the first 24 bits, represents what we call the OUI, the organizationally unique identifier. Okay, and so every manufacturer of network is given an OUI by the IEEE, and so they will use that OUI as the first 24 bits of every MAC address that they burn into their network devices. The last 24 bits are the device identifier. Okay, that's so every one of their devices, every one of their NICs, every one of their switches, Cisco, every one of their switch ports even, is going to have a different address. Okay, now thankfully there's the number of the full number of unique addresses is way beyond anything that we could ever comprehend when we're talking about a 48-bit number. But the idea here, of course, is that every single MAC address on every network device in the world is supposedly unique, supposed to be different. So switches use these addresses to determine where frames are to go. Now, there's different types of addresses. You've got the unicast address, okay, and that just simply represents a single LAN interface, meaning that if I send a frame out of my computer to somebody, I'm trying to reach say a server, okay, and machine knows what the MAC address is, the destination MAC address is for that server, well, it's going to send out a unicast frame, okay, the destination address is specified. There's broadcast addresses, or broadcast address. I mean, the address for broadcast is all Fs. But what that is so that frame is sent to all devices within the broadcast domain. Okay, and just real quick, so basically a broadcast domain is a section of the network in which a broadcast address is sent to those devices. Some definition there, but that's technically accurate. It's when we send out a broadcast, that frame is going to go to all of the machines that are actively connected to that network within that broadcast domain. Okay, so if we're talking about on a switch, you've got 24 machines plugged into that switch. From my machine, that broadcast is going to go to all 24 of those machines on that switch. Now, broadcast, one common use case of broadcast is, say, okay, my machine, I'm trying to talk to a machine with IP address 10.0.0.1, and it looks in its ARP cache. Okay, there's a table within, on my system that has, all of the MAC addresses that it knows. and it doesn't know what the MAC is for the machine that is 10.0.0.1. It's going to send out a broadcast or an ARP request, and that broadcast is going to go to all the machines on that broadcast domain, and whoever has that IP address will respond back and say, hey, that's me. And as the frame comes back through the switch to my machine, my machine will then learn what the MAC address is, and then from that point on, any time the machine talks to that server or 10.0.0.1, it will know its destination address. It can send out a unicast address. Okay, and then multicast addresses are just there's a special use cases. Basically, it's sending out frames, and multiple machines will get that. And that's dependent on, say, if there's a service or something that's running in which all of those machines will be listening for that particular multicast address. Okay. So I'll just leave it at that. We're actually not going to dig into that at all in this, so we'll just move on. So any questions at all?
Questions here. Clean, and Twitter is clean. Nope, you're good.
What was that?
No, I said no. We are good to proceed.
We're clean. Okay, excellent.
Yes, sir.
Okay, so as far as switches, okay, so there's three primary functions of a switch. And we'll look at each of these in depth, but so forwarding and filtering frames, MAC addresses, and creating a loop-free network. Okay, I'll cover the first here in the next few minutes. The loop. That's a whole big topic unto itself. That's when we'll talk about protocol, and we'll get into that close to the end here, if we even get to that tonight. Because and just a heads up, we do have a lot of information to cover tonight that we might have to push off to another time. But we'll see how far we can get. As far as the primary functions, so forwarding and filtering frames. Okay, so the switch, when a switch receives a frame, it's going to inspect the destination address on that frame, and it will compare that address with its own MAC address table. Okay, this is a table within the switch. It basically assigns, or not assigns, but it will determine or learn which ports are associated with which MAC addresses. Okay, and actually, let me show you. I'm going to pull up let's see. So I've got a connection here. I've got a connection into this 5K switch. Okay, and so I'll just show you the address table, and just you can just see what that looks like. So you'll see here that this is these are all the different MAC addresses that this switch has learned. Now on this particular switch, this is, and it's currently we've got a port channel set up on it, and that looks like the only interface that we're currently using to send frames. But all of these different MAC addresses have been learned on this particular. So as frames come in and they have a address, well, it knows to send it out this particular interface, this port channel. So that's just a glimpse at the address table. So again, the address table is just going to list the location of where each of those MAC addresses live. So the whole idea of forwarding and filtering is then, so as the addresses come in, it knows to send it out a specific interface, a specific port on that switch. The filtering aspect of it means that it's not going to send it out any other ports. Okay, and this is a pretty big deal with switches, and that this is how switches are so efficient and so fast because they are just going to send that frame out the very specific port that it needs to go, unless it's a broadcast or flooding, which we'll talk about in a moment. So there's no needless filter, no needless sending it out like the hub does to all the other ports. Okay. Now, as far as the MAC address learning, so I just showed you a MAC address table on a real switch, and it has MAC addresses that have been learned. Okay, so a switch will learn the MAC addresses that are connected or that are associated to each of the different ports as frames come in on those various ports. Okay, so a frame comes in, the switch will look at the source MAC address and say I'm connecting to another machine on my network. I send a frame to the switch, and the switch will see my source MAC address, my MAC address as the source address coming in on, say, port 2. That's the port that I'm plugged into. So it'll add my MAC address then to that port 2. So now when somebody else on the network is trying to reach me, then it knows that, and if a frame comes in with a destination address of my machine, it'll send it out port 2. Okay, it's fairly simple, but that's how a switch learns these MAC addresses. Now, flooding is an interesting concept. So let's say that I have, so I'm trying to reach another machine on the network, and my machine knows what the MAC address is. So it sends a unicast frame to the switch, and let's say the switch doesn't have an entry then on its MAC table for that address. So what it needs to do then is the switch then will actually flood that frame out, all the ports, so that whoever owns that destination address then will respond. Okay, all the other machines in the network that frame gets to, they're just going to drop that frame because they're not the owner of that destination MAC address. But the owner of that will respond, and in his response, he's going to send a reply to the switch. The switch will then see its frame, its responding frame come through, and its source address, or its address will be the source MAC address. So the frame will see that, it'll learn that MAC address, it'll learn its location, and it'll add that to the MAC table. Okay, so that's all that flooding is. It's and there's a difference between flooding and broadcast. Flooding is completely initiated by the switch. Okay, it's again, if the destination MAC address is known by my machine, I mean, well, it's essentially going to be a unicast address, right? The switch will see that, but it just doesn't know. So it's going to initiate the sending out all the ports. Broadcast, on the other hand, is when I don't know what the MAC address is for a machine that I'm trying to reach. So I will send the MAC address with all Fs, send that out, and when the switch receives that, it's automatically just going to send that out to all ports. Okay. So any questions before we move into the next section?
Nope, we are good to go.
Good. Fantastic. Okay.
Oh, actually,
right.
Hold on.
So here we get into.
Hold on 1 second.
Yep.
Okay, Graham. Oh, yeah, it's a comment. And flooding restricted to switch broadcast to the collision domain.
I'm sorry. Repeat that again.
That was a comment from Graham. And flooding restricted to switch broadcast to the collision domain.
Okay.
Not a question, just a comment.
Yep. Sounds good. Fantastic.
Cool.
All righty. So let's let's dive into the last section here, but this is where we're going to spend the bulk of our time. So let's get into VLANs. So VLANs are a big part of the layer 2 switching environment. Okay. So first of all, remember that so switches basically create one big broadcast domain. Okay, if we pull a switch out of a box, by default, it has one VLAN set up on it. It's probably VLAN 1, and that creates one large broadcast domain. You plug multiple machines; they're all going to be on the same VLAN. So a VLAN is essentially it's a virtual LAN. Okay, and what we're doing is we're taking that physical network, so the switch, and we're breaking that up. We're separating or segmenting that into these logical components. Okay, so it's we're just basically setting up these again these logical boundaries within that physical device, and in essence we're then breaking up the broadcast domain. Okay, because each VLAN that is configured on that switch becomes its own separate broadcast domain. So if you see the picture there, I've got a couple machines in VLAN 10, a couple machines in VLAN 20, and so anytime that, say if I've got multiple machines in VLAN 10 and a broadcast address is sent out, it's only going to be received by all the machines in that VLAN. The ones in VLAN 20 won't see anything at all. Okay, so that's a one great use case of VLANs is it helps to control the use of or the frequency of broadcasts throughout the network. Broadcasts are going to be isolated to its own VLAN, so basically smaller sections of the network. Okay, and broadcasts that's activity on the wire, and so there's when there's a lot of broadcast activity, then that can certainly tie up bandwidth on the network. So if we can isolate that to smaller sections, that's just going to be better for network performance. But VLANs are also used for security. Say if we need to logically segment one portion of the network, say you've got a one section, maybe that's your DMZ. Say that this is your DMZ here, and this is your production network here, and we would logically separate those. Probably put a firewall in between them, but that way that there's still a logical separation of those two environments. Okay, so security is a big reason to use VLANs. As far as management, there's oftentimes there's a need to break out the network into various work groups, or say if you want a dev, a production, there's just some more efficient management control when you're breaking out those networks into different VLANs, and then troubleshooting. If there's a problem in one section of the network, one VLAN, it's much easier to find the source of the problem when you're just focusing on one particular VLAN. Let's see. Now, let's go back to this. Well, first of all, why don't we just I'll go through. Let's see. I'm going to pull up let's do this. I'm going to pull up a different switch here. And so we just want to look at just a real quick look at different VLANs on a machine. This particular switch already has some VLANs already configured on it, but we can always create a VLAN. It's very easy to do within a switch. So if I just want to create VLAN 10, I'm already in the configuration, so configure terminal. Point within the switch, and then I just do the command VLAN 10. That just created a VLAN. and then I'm in the VLAN subcommand. And if I just want to give it a name, we'll do, let's do development. Okay. And then if we show VLANs again, we'll see that I've got my development VLAN. Okay. So super simple to create VLANs. Now, let's say we had our VLANs 10 and VLANs 20, or VLANs 10 and 20. And we need those machines and those two VLANs to be able to talk to each other. Okay, so let's move that out of the way. Let's pull this back up. So how do we forward data then between VLANs? Well, okay, we are going to creep up into the layer 3 of the OSI, the network layer, because that's where we need to do what we call inter-VLAN routing. Okay, so we actually, there's an actual routing function that has to take place in order to get the frames from my VLAN to VLAN 20. Okay. So in order to do that, there's two ways we can go about that. One is we could actually pull in a router. I don't have a picture here, but if you can imagine, say, a nice little round router up here, right above the switch, and if we could have one of its interfaces connected down into the switch for VLAN 10, and then another interface that's on VLAN 20 also going up to the router. Then the router can be used to simply route the packets from the subnet for VLAN 20 to the subnet for VLAN 10. Okay, and that's a nice, easy way to get traffic from one VLAN to another. Now, challenges with that are that it becomes a performance issue. I mean, we're basically adding 2 additional hops to the network path in order to get traffic from one VLAN to another. So the way that we decrease the number of hops and potentially get as much performance is by bringing that routing functionality into the switch. So we go back here, we look at this, and so if all of that's just taking place within the switch, okay, we're removing the bottleneck of the additional network links, and so that traffic can go across through that switch much faster, and so that switch can then basically do its layer 3 routing of frames from one VLAN to another. Okay, so in order to do that, let's go back to our switch over here, and so let's see. Just want to check to make sure. One of the things about Nexus switches is there are a lot of features that are disabled right out of the box, and the idea is that basically, if it's not needed, then don't. There's no reason for it to be using up any of the additional resources. So basically, disable as many services as you can until you need them. So the service that we're looking for is interface VLAN right there. Okay, and that is disabled right now. So in order for me to be able to set up what we call a switch virtual interface, and we need that in order to do inter-VLAN routing, I need to enable that particular feature. Okay, so it's very simple. It's the feature command, and okay, so feature interface -VLAN. And then if we do a show feature again, I'm just going to take a look just to make sure that that is truly enabled. And it is. So at this point, I just want to make sure that I'm on the right switch. I was looking for VLAN 10, my development VLAN. So I'm going to do an interface VLAN 10 command. Okay, now I'm in the interface subcommand for that VLAN, and now I just need to give it an IP address, and I'm just going to give it just a random IP address, and for the subnet mask, we just use the CIDR notation, so I'm just going to give it a /24, just a normal 255.255.255.0, subnet mask, and that is, so I've created the interface for the VLAN 10. I've given it the IP address, and I can even give it a quick description. Let's call it dev. Okay. Now at this point, so if I show, if you look here, you'll see the VLAN 10 is still administratively down. Line protocol is down. Okay. So one additional step I need to put in there is the no shutdown command, and that basically that will enable that. Let's see. It's not the command. There's another command I remember that would actually show. Let's see. Yeah, well, anyhow, I'd have to go back and I'll tell you, I'm still learning this stuff too, guys. So, but essentially, we would be bringing that that interface back up, and so then if we've got, say if I've got a VLAN 20 on that switch as well, I would create an SDI, a VLAN interface for VLAN 20, and then I'd be able to basically route data from one VLAN to the other. Okay. Okay. So 802.q. All right. This is the network standard that supports VLANs. Okay. It's the default standard trunking protocol, and it looks like, Chris, I think you got my machine.
Sorry about that. Yeah, I was tracing the disregard.
Yeah,
I moved off again.
Sure. Okay, so so again, 802.1q, the default standard trunking protocol. Okay, it's the standard that basically defines the VLAN headers, VLAN tags. We'll look at native VLAN here in a moment also. But it's interesting. So 802.1q is an IEEE standard. Cisco also has its alternative to 802.1q. It's ISO. And interestingly, so on the Cisco iOS switches, when you create a trunk port, you have to set the encapsulation mode for either ISL or 802.1q. Okay, most deployments I've ever seen, it uses the .1q encapsulation mode, which is 802.1q. And because of that, even though that's the Cisco proprietary trunking protocol, Nexus only provides support for 802.1q, the IEEE standard. So interestingly, when we create a trunk port on a Nexus switch, if you're familiar with configuring that trunk on an iOS switch, you always have to set that encapsulation mode. Well, there's no command for that on the Nexus side. So anyway, just an interesting thing there. But 802.1q, again, that is the standard that supports those VLANs, and this is how it does it. It's using a VLAN header, and that VLAN header becomes part of the frame, part of the Ethernet frame. Okay, and you see the picture down below here. So this is the frame header. You've got your destination MAC address, your source MAC address, and then you've got the 802.1q header, the VLAN header, and then some additional information here, and of course the data payload, and then the correction, the control portion of the frame. But the 802.1q header that's where you will find the VLAN number, the VLAN ID. Okay, and now that is a 4-byte field within the header. It is of those 4 bytes, 12 bits of that represents the actual VLAN ID number. Okay, and you do the binary math, 2 to the 12th power gets you 4096. So we can have up to 4096 VLANs, or I guess technically 4094, since 2 of those numbers, 0 and 4095, are reserved. Okay, so in most environments, unless you're a service provider, you'll never get anywhere near using up that number of VLANs. But that is how frames are tagged with a VLAN. So we talked about VLAN tagging. This is where it takes place. This is how it's represented within the header of that frame. Okay. So as far as the different modes within a switch, okay, so typically we would be, we're going to be using a VLAN tags one way or another, okay. In access mode, if we're setting up a switch with a port in access mode, we're going to assign a VLAN to that switch port, okay. So say the access port is it's access VLAN 10. Okay, so and my machine's plugged into that, then my machine is living on VLAN 10. Okay, access mode allows only frames with just one VLAN. So my machine then will send frames to that switch, to that access port. And those frames coming from my machine are untagged. Okay, there's no VLAN tag on it. But once they get to the frame, VLAN tag is added, and then depending on where it exits, which port it goes out of on the other side, if it goes out another access port, then the VLAN tag will be removed so that it goes back out on the wire as an untagged frame. Trunk mode, on the other hand, can carry frames from multiple VLANs. Okay, you've got a single port on the switch, and we can configure that port to have to carry traffic for any number of different VLANs. So you can do all VLANs if you want. Typically, you will set a trunk port to very specific VLANs. Okay, that's really the best practice when using trunk ports. You want to define what traffic can go across that switch port. So if we have a trunk port set up and say, let's say we're in a VMware environment, host servers, we've got a host server that's got, it's one of its physical nexus connected to the switch into a trunk port, then from the host server, it will send frames from that host server to the switch with VLAN tags. Okay, it's actually going to come into the switch with a tag on it, because at that point the trunk will look, or the switch will look at that frame. It'll see the tag, and then it'll know which VLAN to pass that frame on to. Okay. And then, so if we want to look at our switch again, okay, so let's configure. Okay, I'm actually just going to grab one of these random. I'll use about Ethernet 1.8. So I'm going to configure so port Ethernet 1.8, and even though there's no SFP in that port, I can still configure that port to either be an access port or a trunk port. So in order for me to configure that as an access port, I can just do access VLAN 10. Okay. Now that particular port is now set up. Let's see. Sure. Okay. So that port is, again, I've got it configured as an access port. So allowing traffic for VLAN 10. And just want to check one thing here. Okay, so we're looking at some of the details of this particular port. We can see that the operational mode of this is an access port. Access mode VLAN is 10. Okay. So now let's say if we wanted to instead make this a trunk port. Okay. So first of all, I'm just going to remove the okay, and then I'm just going to make it a switch port. Let's make that. So I just made that switch port a trunk port, and I'm going to allow. Let's see, VLAN allowed. Oops. Okay. So I just created configured that switch port as a trunk port, and I'm allowing VLAN 10 to go across that trunk port. Okay. So then if we look at the details of that, we'll see that it is a trunk port allowing VLANs 10 to go across it. Okay. So let's say I'm just going to create another VLAN, and now let's say I want to add VLAN 20 to that trunk port. Okay. So interface Ethernet 1.8. So I'm in the interface subcommand, and I'm going to just do the switch port trunk allowed VLAN add. Yep, add 20. Okay, so now I'm just adding VLAN 20 to that trunk port. So then if we, again, check the details of that port, we'll see that I have VLANs 10 and 20 going across that trunk port. Okay, now. So in these details, you also see this thing here. It's trunking native mode VLAN. Okay, there's a native VLAN 1 on this trunk port. So so the whole concept of a native VLAN is so you've got a trunk port, and now remember that trunk ports require frames to come in with a VLAN tag in order to be able to pass them on to various VLANs. But what happens when a port or when a frame comes in and it does not have the native, or it doesn't have a VLAN tag? Well, then it automatically is forwarded to the native VLAN. Okay, and essentially what this does is, so at that point it becomes part of, in this case, the native VLAN is VLAN 1. It becomes part of VLAN 1, so it can then actually talk to any of the ports that are configured for VLAN 1. Okay, now the purpose of this is basically to provide some management functionality. Say if you're plugging in, if you're using Telnet to get to the switch, or using some means just to connect to that switch, and you don't have the means for creating adding a VLAN tag. Okay, plug it in. You're on VLAN 1. You can do your management actions, and it basically provides that mechanism to get around the requirement of having a VLAN tag. Now, this basically it can certainly become a security hole for that switch, and so really security best practice is to change that VLAN to one that's not being used by any active network device on that network. So basically, you can't get rid of the native VLAN. You have to set up some native VLAN, but you can use it on one that's not actively being used. Okay, that way you don't have some rogue device connecting to the network, getting onto that native VLAN, and then being able to wreak havoc by connecting to other network devices that are on that particular VLAN. Okay. So let's see. Chris, we're getting close to the hour. Do we have questions at this point?
We have a comment from Graham. He made a comment about VLANs, that there are some other reserved VLANs for Cisco environments for fiber channel, etc.
Yes. Yes. Good point. Yep.
Other than that, let me check the tweet decks. And no, we are good. We are clean of questions, sir.
Okay. All right. So I tell you what. Let's. I'm going to get through VLAN trunking protocol. Won't take me a whole long time to get through. But then there's a spanning tree. Spanning tree again. It's its own monster. So
yeah.
So I'm not going to tie up everybody's time tonight by going into that. But let's get through VTP.
Yeah, sure. Let's get through that.
Okay. So VLAN trunking protocol. Okay. Essentially, what this is it's a way of being able to make a change on a VLAN change on one switch and have that propagate out to all other switches. So a good convenient way to distribute the VLAN configuration. So let's say you've got 20 switches in your environment, and you need to add a VLAN. You need to add it to all the switches. You can effectively make that change on the one switch, and then all the other switches will basically be updated with that change. Okay, so it's a great, very powerful functionality, and it certainly time saving. It can be potentially error preventing. So if you've got, again, you're making if you need to make one change on all of the switches, well, the more switches you have to do, the greater your chance of fingering one of those configurations. So it's a nice little way of automating that process down the line. Now, of course, that also comes with its risks. If you make an error on your configuration on one switch, well, that error can then get propagated throughout the rest of the network. If you accidentally delete a VLAN on one switch, and that's a critical VLAN, well, then suddenly that VLAN is lost on all the other switches as well. So you can, take down portions of the network. So, and I've also heard stories where somebody has pulled a switch out from the lab environment. It used to be on the production, and they plug it back into the production network, and because of the way that VLAN or VTP works, and let's say it's a lot of VLAN changes have been made on that switch, that switch could potentially update all the other production switches on that network with its whatever VLAN configuration it had from the lab environment. Okay, so hopefully that wouldn't happen. I've heard though of that, of real occurrences of that. So anyway, just
have you really? Wow.
Yeah, I've I mean it's I can't remember who it was in one of their training videos that mentioned that occurring. But in any case, yeah. So it's something that needs to be used with great caution. The NOS it's disabled by default. But the way that it works, so let's get into the basics here. It's so all of the switches in the VTP domain. Okay, the VTP domain is essentially all of the switches that are participating in this VTP. So they all need to have the same VTP domain. A password needs to be set up. Okay, so then and so all of the switches in that domain have the same password, and then each one of those the switches needs to be configured as either a server or a client. Okay, so the difference there, if it's in a server mode, then you can create and modify VLANs all day, and then those will then get propagated out to the clients and other servers. If it's in a client mode, you cannot make any changes to the VLAN. They are only there to receive updates from other servers. Okay, so a big distinction there. I mean, servers can update from other servers. You can make changes on a server. Client will receive all the updates from any other server, any other client, and you just can't make any changes there. Now, the way that it goes about updating, so if any little change is made to a VLAN, that entire VLAN database is then the configuration information of that entire VLAN database is then sent out to all of the other switches in that VTP domain. And they use a revision number. Okay, so it's every change that's made on a VTP server, it increments the revision by 1, and then it sends out the update in the entire VLAN database, sent out to all the other switches, and the goal then is for all the switches on a VTP domain to have the same version number of that VLAN database. So it's, again, fairly powerful process. And here I'll show you on my switch here. Let's see. Not sure if I set a VTP on this one yet or not. Okay, so you can see here that VTP is disabled. So in order to enable that, I'm just going to do a feature VTP. So it's now, it's now enabled. And so then to set up, actually, let's just take a look at VTP status. So on this machine, on this particular switch, you can see that these are the default settings. Operating mode by default, when you turn on VTP, it automatically is set in server mode. We can change that to client. And let's see the domain name. We would need to manually set that. There's some other things here. VTP version, we can actually change that to 2. The difference is there's some differences. Right off the top of my head, I'm not sure the exact differences, but we can always change that from version 1 to version 2. And then, so to set the, let's just say we're going to set the domain to production, spell it, and then I'm just going to set the password, and you'll see it's clear text there. That's great. And so let's just do show. Okay, so again, pretty easy. I just set the domain to production, and then if we just wanted to change this, let's say we already have another VTP server on the network, and I just want to make this a VTP client, then we can just do VTP, I think it's mode, client, and we've just made this a client. So if we go back to the status, you'll see that we're now in client mode. So I will not be able to make any, let's see if we can add a, nope. So I just tried to add a VLAN. I'm in VTP client mode, and it says that I cannot add that VLAN because it's not allowed when I am in VTP client mode. So, okay, so a couple more things about VTP. There are some alternate modes. Okay, so there's VTP transparent mode, and what that does is basically, if let's say we've got five switches on the network, one of them is in between a couple other switches that I want to have participating in VTP. That particular switch, and here I'll show you a picture here. Let's say that here's my switch. I've got a couple others here that I want to make sure are participating in VTP. So any change made to this VTP server, I want to make sure that VTP client down here gets those changes. But this one here, I want this to be independent for whatever reason. you know, I can make changes on that. I don't want this one to be updated by the changes on this switch. So I can put this switch into VTP transparent mode. It will still send my VTP updates through it, but it will not actively change or get updated by the rest of the switches in this domain. Okay, so again, this one stays pretty independent. I could also leave a switch out of the VTP domain. So this one's not even basically its VTP functionality is turned off, so it's not going to get any of the changes from the rest of these VTP switches. Okay, so again, this one, I'll be able to make changes all day on this. It will have no impact on these other guys. And even over here for the VTP transparent, I can make changes on this one, and it will have no impact on the clients. Okay, and all right. So the last section is spanning tree protocol, and because that's probably take a whole nother hour to go through all the rules and all the fun stuff with that, I'm going to spare you guys that tonight.
Yeah,
so,
what we'll do is we'll glom the two together. We'll finish the rest of the recording offline at a later date, and then
sounds good.
Merge the two into one section 2 video for the website. Cool. Graham had a couple of comments about VTPs.
Yes.
Support the same VTP version, otherwise the higher number of VLANs will propagate, and VTP supports VLANs over 1001 and PVLANs.
That's right, yep. Good.
Wanted to make sure that got said.
Yep.
Cool. Okay, so I'm gonna kill. I'm sorry. Graham said VTP 3 does. Sorry.
Okay.
we're all learning
That's
tonight.
Good to know also. Absolutely. This is good stuff.
Cool. Okay, so I'm gonna go ahead and stop the recording now. And